Hi, everyone. This is Nick Fryer, and today we're talking about Physics 2, Lab 4, which has to do with bar magnets. So, just as an introduction, we ran an experiment where we observed how changes in distance affect the magnetic field measurements at different locations. We measured the magnetic field both on axis and off axis in the 45-degree angle and the 90-degree angle, so perpendicular. And then we used a computational model to simulate the experiment and compare the measurements versus the simulated measurements. In conclusion, the net magnetic field's magnitude is generally inversely correlated with distance. The magnetic dipole moment was measured to be 1.833 ampere meters squared. The magnetic field off axis was about 8.466 times 10 to the negative 5 Teslas. And on axis, depending on the distance, it ranged from about 2 times 10 to the negative 5 to 2 times 10 to the negative 4 Teslas. So just as some fundamental principles, the biggest one being the Biot-Savart law, which has to do with magnetic field. It claims that magnetic field is produced by an object at an observation point that depends on both the current running through the object, which is I, and the distance from the source to the observation point, which is R. And far from the source, we have that the magnetic field of a loop is approximately that of a dipole. In this case, the bar magnet is the dipole. Where we notice that mu is I times the cross-sectional loop area. So in this case, our loop or our dipole was a cylinder, so it's the area is pi r squared. And then the direction of the magnetic field of the loop is in the same direction as mu, so south to north. Related is the dipole or the perpendicular dipole magnetic field, which is about half of the magnitude of that of the parallel dipole, but it's in the opposite direction, so opposite of mu. And then the magnitude of the magnetic field of a bar magnet in general is k times r to the power of n, and we calculate r later. So here we just have a very basic system, a little diagram. So we notice that mu points from south to north, and then the rest are the approximate magnetic field lines at each observation point. So in the experiment, we had a bar magnet, a magnetometer, which was on the phone, and then tape and a meter stick. We turned the phone towards magnetic north, which is the angle where the x component was 0. We found the location of the magnetometer in the phone by maxing out the x and y components at different points. And then we measured the magnetic field on axis. So we found the distance that it took for the magnet to reach different values on the phone. And then off axis, we recorded the distance from the magnet where the magnetic field in the x direction was 100 Teslas. Then we recorded the magnetic field in the y direction with no bar magnet. Then we moved the magnet to the recorded distance from before in the x and y components, which is a 45-degree angle. And then we measured the magnetic field again. So this is just some quick data. We notice a linear correlation between the magnetic field and the distance when we took the natural log of both. And then just as some quick observations, at a large distance on axis, the magnetic field was nearly 0 in the x direction, but as distance decreased, the magnetic field increased. So just as some data analysis, we were given the regression line with a slope and a y-intercept. We took that y-intercept, which is the natural log of k, and then we produced a k based off of that, which we then used to calculate mu, our magnetic dipole moment, which was 1.8 ampere meters squared. So this is just our computational model. You can see the different values that we used in functions. This is more computational model. And then these are the results. So we see a very big error in the 45-degree angle, but otherwise relatively good. So just as some discussion, as the distance increased, the magnitude of the net magnetic field decreased. So to get to 20 Teslas, we needed a further distance than we did to get to 170 Teslas. The magnetic dipole moment, again, was measured to be mu as 1.833 ampere meters squared. And off axis, the magnetic field varied a very decent amount, 43.68% between the experiment and the glow script model. So that could be due to a lot of sources of error. One is the presence of other magnetic objects that were in the lab, so phones, laptops, other magnets that different groups were using, etc., as well as an incorrect location of the magnetometer in the phone, which was a very non-mechanical process. It was hard to find. And measurement error. So the magnetometer readings were constantly fluctuating, so it's hard to find exactly where BX took on some exact value or what the exact value was. And distances were only accurate to 1 decimal point because of the meter stick we were given. So if we hadn't oriented our experiment to compensate for magnetic north, in the x and y components, the magnetic field would likely change because now magnetic north is contributing. So this affects both the x and y components, but the z component probably wouldn't because Keeping the phone flat doesn't really change the Z orientation. So if we stuck two identical magnets together end to end and we ran the experiment again, the net magnetic field would likely increase in magnitude, probably about double, although distances slightly change because now the center of the dipole is a little bit different. And the distances needed to reach a certain magnitude would increase because now our magnet is stronger. So we don't need to be as close to get the same magnitude value as we would for only one. Thank you.